Welcome back. We're now into the tree data structure section, right over here. And as we can see, trees or linked lists are a type of a tree that we've already talked about. But there's a few others over here that we have yet to talk about. So we're going to cover that and get familiar with the main different types by starting off with binary tree. Let's get into it. A binary tree is something you've likely seen before. And it's a type of tree with a few rules that are applied to it. But they're quite straightforward. Each node can only have either 0, 1, or 2 nodes. And each child can only have one parent. This is a binary tree. However, this is not a binary tree because it has 3 children, or at least one of the nodes has 3 children. And each node represents a certain state. And this is very similar to what we've done in the past, especially with linked lists. If we take a look at an example here, in order for me to create a binary tree, well, I can just create a function, say binary tree. And this binary tree perhaps will get a value. And the binary tree, or in our case, let's just do a binary tree node, will simply have a this.value associated with it, which is the value that we give it inside of the function. And then we have 2 other properties, which is a pointer to the left side of the tree, which for now will be null, and a pointer to the right side of the tree, that is this.right equals null. And that's it. We can represent a binary tree node as simply having a value and then a left and a right property. Very similar to what we did, or a very similar principle to what we did with linked lists. Now, we're going to actually code a tree and create a tree data structure just like we have for past data structures. But I want to also point out a few terminology that we might come across and that are important. In this case, we're looking at something called a tree that is completely full. That means there are no gaps in the tree. Let me show you what I mean. A perfect binary tree has everything filled in. That means all the leaf nodes are full, and there's no node that only has one child. A node either has 0 children or 2 children. And also, the bottom layer of the tree is completely filled. Nothing's missing. Versus a full binary tree, which simply says that a node has either 0 or 2 children, but never one child. Now, why is this important? Because this type of binary tree, especially a perfect binary tree, is really, really efficient and something that is desirable. When binary trees are perfect like this, they have 2 really interesting properties. One is that the number of total nodes on each level doubles as we move down the tree. For example, here we have 1 node. In the next level, we have 2. So we've just doubled the nodes. In the next level, we have 1, 2, 3, 4. So we've doubled 2 to 4. If we had another level that's a perfect binary tree, we'd have 1, 2, 3, 4, 5, 6, 7, 8. So we were doubling every time. The second important property is that the number of nodes on the last level is equal to the sum of the number of nodes on all the other levels plus 1. All right, that was confusing. What do I mean? Well, here, if I take the bottom level, that is 1, 2, 3, 4, the second property states that all the nodes above it plus 1 is going to equal the bottom level. So 1, 2, 3 plus 1 equals 4. That is what we had on the bottom. Which means, in other words, that about half of our nodes are on the last level. And this brings up a really interesting point. By organizing our data in this way, we have half of this data in the bottom level. If somehow we can avoid visiting every node even if the node we're looking for is at the very bottom, perhaps there is some efficiencies that we can have. And you'd be right. Because of this type of structure, you're going to see a new notation of big O, something that we've been waiting for a long time, O log n. And when we start talking about something called binary search trees, you're going to start seeing this notation. Yes, we finally got into another big O notation, but what does it mean? In the next video, I want to talk about O log n and why trees allow us to have something like this and what the implications are. I'll see you in the next one. Bye-bye.